vapor pressure of solutions. So till now, we've been talking about the vapor pressure of just pure liquids. What about when we have a solution? So adding a solute to create a solution lowers the vapor pressure and therefore raises the boiling point. So the key here is that if you add a solute, you lower the vapor pressure. Why? Because when you add a solute, don't you have attractions between the solute and solvent particles, right? The solvent has to surround or solvate the solute particle or molecule. So the attractions between solute and solvent result in less evaporation of the solvent molecules. And if less solvent molecules can evaporate, then the vapor pressure is lower. By the way, this leads us to that incorrect thought that adding salt to water raises the boiling point, okay, right? Decreases the vapor pressure and therefore raises the boiling point. And raising the boiling point speeds up cooking, right? In theory, that's true. You add salt to the water, you lower the vapor pressure, you increase the boiling point. The higher the boiling point, the faster it cooks. But actually this isn't true because you'd have to add a lot of salt to the water to actually have a measurable effect on the boiling point. So salt is added for reasons unrelated to this. Okay, so here we see attractions between the ions of sodium chloride and water that reduce the evaporation of the water molecules and therefore the vapor pressure. So on the left, you see just pure water. Once the hydrogen bonding between the water molecules is overcome, the water molecules can evaporate and exert a vapor pressure at the top of the liquid. In the 0.1 molar sodium chloride solution, though, some of these water molecules are tied up in solvating the ions, right? And if they're tied up in solvating the ions, they're not available to evaporate, okay? So a smaller number of water molecules evaporates, and a smaller number of water molecules exerts a pressure on the top of the liquid, which results in a lower vapor pressure. The amount of solute particles produced per solute molecule is called the Van 't Hoff factor, VHF. The higher the VHF, the greater the impact on the colligative properties of the solution. So in other words, the more ions or the more particles, you have per solute molecule, the greater the effect. So starting with molecular solutes or covalent solutes, they don't dissociate into ions, right? So they have Van 't Hoff factors of 1. So methanol, glucose, and this other one we've been talking about, CH3CO, CH3, all covalent or molecular. They don't separate into ions, and so they have a Van 't Hoff factor, VHF, of 1. Ionic solutes have Van 't Hoff factors that correlate to the number of ions present. So sodium chloride separates into 2 ions, Na plus and Cl minus, so it has a VHF of 2. Aluminum nitrate is 3 nitrate ions for every 1 aluminum ion, and that would be a total of 4 ions. So it has a VHF of 4. A quantity of aluminum nitrate will have 4 times the impact of a molecular solute and 2 times the impact of NaCl on the vapor pressure of the solution. So if I had equimolar concentrations of, say, glucose, sodium chloride, and aluminum nitrate, I would expect a 4 times change in the vapor pressure for the aluminum nitrate as opposed to the glucose, and twice as much for the NaCl, or twice as much as the NaCl.